At the end of the last session, we talked about this problem of a bank with two branches. And let's just revisit that. So let's say that I have one branch here in Hong Kong, and let's say there is another branch in London. And we said that people can deposit money in Hong Kong and they want to get their money back in London later. Now, the idea was that the Hong Kong branch can send only one message to the London branch, and this message, we called it M. We said that this is sent over an unsecure channel. So my assumption is that this message M can be seen by anyone. Maybe a hacker sees it and then publishes it to everyone, but no one can change it, okay? And we will talk about digital signatures later on, but for now, just imagine that this message somehow has a signature from Hong Kong and it's impossible to forge that, okay? So this is what we have. And then we have a bunch of people who are depositing money. So let's say, again, we have Alice, Bob, maybe Carol, and let's say Dave. And each of them is depositing some amount, maybe 50, 100, 200, and maybe 10, right? And then later on, they want to be able to go to the other branch and get their money back. And we said that the Hong Kong branch should give each one of these people a proof. So let's call it P1, P2, P3, and P4. And generally, whenever I don't say what the type of something is, you should just assume that it's a string of zeros and ones. So the message M that I'm sending from Hong Kong to London is just a string of zeros and ones. The proofs that I'm giving to each one of the depositors, these are also just strings of zeros and ones. And then the idea was that, let's say this happens on day one. So on day one, everyone does the deposit, and then the Hong Kong branch gives them the proofs. And then let's say the next day, on day two, each one of them go to the London branch. The London branch has already received the message M, but now each of them should be able to give the proofs that they have received from Hong Kong to the London branch and get their money. Now, if we want to write our requirements more specifically, these are the requirements that I have. I have to make sure that everyone can get their money back, and I have to make sure that they can get their money back only once. So you shouldn't be able to deposit once and then withdraw twice. So let's say the first one is that every depositor can withdraw. But the second constraint is that each deposit can be withdrawn at most once. Okay. And we will later on see that this is actually one of the most problematic issues when we're designing a cryptocurrency. So this is the problem of double spending. Maybe someone has just one coin and they're trying to use it twice or something like that. Here we will have someone who has deposited once. Let's say Alice has deposited $50, and maybe she goes to the London branch and then she tries to withdraw $50 twice. We have to make sure this cannot happen. And the other constraints that we want to have is basically, I don't want to leak any data based on M. So M is public, everyone can see M. No one should be able to find any of the personal information of the depositors and the amounts that they deposited based on M. So M does not leak any personal data. Okay. And then we also talked about this idea that maybe this channel is really expensive. Maybe I want my message M to be as short as possible. So this is another requirement. I just want to say that the message M is really small. So let's say M has constant length, has O1. This is another thing that I would like to have. Because otherwise, if M could be large, well, the Hong Kong branch could just take the hash of every transaction, the hash of every deposit, and send all of these hashes to the London branch, right? That would make the problem trivial, but at the same time, we have a really huge M. Now, we saw a solution last time, and the solution was to just use a linked list or a ledger with hash pointers. So the idea was very simple. This was our initial idea. So maybe I can call it non-solution one, because we know that it will not work in the end. Was that I'll just create some transactions, and let's say every transaction has some ID and let's say this is transaction number one, and let's say it also has a pointer to the previous transaction. Now, in this case, because there is no previous transaction, this pointer is just null. There is nothing in there. But then in this transaction, I say who paid the money and how much. So maybe I just say this is Alice and 50. Then I create another transaction. It's really hard to so this was transaction one. This is my transaction two. It has a serial number 2. It should also have a pointer to the previous transaction. So it will have a pointer to this transaction. And basically the way that works is that I have a hash of the previous transaction. So the pointer is just a hash of transaction 1. And then in transaction 2, I'm saying that Bob paid 100. So I would just write Bob 100. And I just repeat this for the other 2 transactions as well. So I have transaction 3, and this one is Carol. What was the amount? 200 and then 10. Okay, so 200, and it also includes the hash of the previous transaction. And then finally, I have this last transaction, transaction 4. It has the hash of transaction 3. And it says that Dave paid much 10. Okay. Now the question was, what is the proof that we can give to each of the depositors, and what is the message M that we're going to send to the other branch? So for the message M, we said we just take the hash of the very last transaction. So I just take this whole transaction, I hash it, I get hash of transaction 4, and I say this is my message M. And I send this to the other branch. Now, let's say that you're one of these depositors and you need to go to the London branch and prove that one of these transactions actually exists. It's actually in this list. Now, let's say you're Dave. If you're Dave, you can just go to the other branch and you can just show your transaction, and they can just calculate the hash. They see that it's the same as M that they received from the other branch, so they know that you didn't fake this transaction. So they would give you the money. But now, imagine you're Carol. If you're Carol, you can't just give your own transaction. You have to also provide Dave's transaction, because that's the only way you can verify Carol's transaction here. See, as the London branch, you know M. You know the hash of this last transaction. So if Carol wants to prove that this transaction, transaction 3, actually, I forgot to write the transaction name. So this was transaction 3, this is transaction 4. If Carol wants to prove that this transaction is actually in the list, she has to start from the end of the list. She has to first say, here's transaction 4, which has the correct hash, and the bank can check that. And then she has to say, okay, now in transaction 4, as you see, there is a hash pointer to transaction 3. And here's transaction 3, and now you can check that it has the correct hash. So that's how Carol can prove that her transaction is in there. So in order for Carol to prove the existence of her transaction in this list, she has to actually know her own transaction, but also Dave's transaction. Now, the problem becomes even worse for Bob, because you can just continue with this. Bob has to know his own transaction, Carol's transaction, and Dave's transaction. In general, each person who wants to prove the existence of their transaction has to also prove every transaction that comes after it, right? So in general, the proof that I'm going to have, if I have n transactions, I don't know why this writing is not working. Okay, so assuming that I have n transactions, this is what happens. The proof of transaction I is going to include transaction I itself, but also transaction I plus 1, transaction I plus 2, all the way to transaction N. Right? So this is the proof that I'm giving to each one of my depositors. So Alice here is going to have the longest proof because she actually needs to have all of the transactions in order to prove the existence of her loan. Now, two problems, and these were the problems that I mentioned at the end of the previous session. The first problem is that now our proofs are too long. And the second problem is privacy. If Alice needs to know all of the transactions that come after hers in order to prove the existence of her transaction, that means that Alice has to know that Bob deposited 100 and Carol deposited 200 and so on. So Alice knows everyone's name and amounts that they transacted, and well, that's not something that we would be happy with. So let's add some extra requirements here. I can apparently only write towards the top of the page for some reason. Okay, so my extra requirements are going to be short proofs and privacy. So short proofs is fine. Privacy, by privacy at this point, I mean that no one should be able to see other people's transactions. So no one should be able to see other people's names, and no one should be able to also see the amounts that they deposited. So no client sees other people's information. But are these the only requirements that are not satisfied? Can we just check that these previous requirements are already all satisfied? So every depositor can withdraw, yes, because every depositor can prove that their transaction was actually in the linked list in the ledger. So we have this one. Each deposit can be withdrawn at most once. Well, this one is something that we can enforce on the side of the London branch, because the London branch can just remember which transactions have been paid out and just don't pay out the same transaction more than once, right? And every transaction has a serial number, so they can just keep track of the serial numbers that are paid out. So this is easy. Now, here's the interesting part. We already had the requirement that M, the message that is sent from Hong Kong to London, does not leak any information, any of the personal information of the people. And actually, we satisfied that because M is just the hash of this transaction, right? And hopefully the hash of the transaction doesn't really leak any information. But in the last session, we saw that if you don't have nonces in your hash, it can actually leak information, right? But here, I don't need to add an extra nonce, because this hash is pretty much like a nonce itself, right? So the hash of transaction 3 is already included in transaction 4. And that's something that really makes our domain large. So no one can really do any kind of butterfly attack or just trying every possibility, brute forcing, things like that. But if you don't trust your hash function, you can also add a nonce here. That's fine. So this makes sure that M does not leak any information. And of course, M's length was fixed because the output of a hash function always has a fixed length, let's say 256. So this is also fine. Now, the thing that is interesting here is that I didn't want M to leak any personal data. And basically, I used the hiding property of the hash function here. I said that because M is just the hash of something, and because my hash function is hiding, this M is not going to leak any information, right? So now here, for privacy, I need something very similar. It's just that I want to make sure that none of the clients can see anyone else's information. So maybe I can again use hashes. So the idea here is to use hash to hide data. Okay. So what was our problem here? Why were we leaking any personal information? Basically, the problem was that when Carol wanted to prove that her transaction is in there, she had to also provide the transaction for Dave. But then the transaction of Dave actually included his name and his amount, right? So if I just define my transactions in a different way, so that my transactions don't have this personal information in them, but they only have, let's say, the hash of the personal information, then no information will be leaked. So let's do this. Let's say that, first of all, I need a bunch of nonces for my hashes. So let's say whenever someone is depositing money, they're also giving a random nonce to the branch. So Alice, when she deposits the money, she chooses some nonce N1 and also gives this nonce to the Hong Kong branch. And let's say this N1 is just a random string of 1024 bits. And let's say Bob does the same thing, Carol does the same thing, and Dave also does this. Now, I'm going to change the structure of my transactions. So this is non-solution 2. It's going to solve our privacy issue, but it's not going to solve the problem with really long proofs. Now, again, look here. Transaction 1 used to include the personal information of Alice. Instead, I'm just going to say this transaction will only have the hash of the personal information. So I'm going to create a new transaction 1. And again, just as before, it has a serial number, it has a pointer to the previous transaction, but there is no previous transaction, so this one is null. So when I say null, you can just imagine a string of all zeros, right? And then here, instead of actually putting Alice 50, I put the hash of the string that contains her name, and then concatenated with the amount, and then concatenated with the nonce that she chose. Okay. So this is now my new structure for my transactions. And of course, I do the same thing for the other transactions. So this is my transaction 2. And let's say transaction 3 and transaction 4. And each one of them will have a serial number. It will have a pointer to the previous transaction, which is basically just the hash of the previous transaction. And instead of the information, it will just have the hash of the information. So Bob 100 and the nonce of Bob. And 2. Okay. And so on. I'm just too lazy to draw this, you know. Okay. Now, first of all, why do we need the nonces? We need the nonces because otherwise, again, someone can do a brute force attack. If someone knows the names of all of our clients, they can just try every possible name, and they can also try every possible value if the values are small. So we need the nonces here to really hide the data. But now, actually, my laziness is backfiring. I have to actually put them here, I guess. So I have this hash of whatever here, hash of the personal information. I have a pointer to the previous one. I have a serial number. And here again, I have the hash. I have a serial number, and I have a pointer to the previous one. Okay. Now, just as before, we have to talk about what kind of proof we have to give to each one of the depositors. So the last depositor, again, just brings the transaction. So I just say that my M is the hash of this last transaction. So that's the value that the Hong Kong branch is sending to the London branch. And if the last depositor wants to prove that their transaction is in the disk, they can just bring their transaction. And when they bring their transaction, the Hong Kong branch can check that it has the right hash. And then when they see that it has the right hash, what is it that I'm providing? I'm basically providing this pointer, this serial number, and this other hash. But now the London branch is convinced about this hash. right? But this hash is the hash of my personal information. So it's the hash of my name and the amounts that I put in and the nonce that I chose. But I know all of those things. So I can give those things to the London branch as well, and they can verify it, and they can know that this was the amount that I put in. So the proofs actually work just like before. So now let's consider Alice. Let's say that Alice wants to prove that transaction 1 was in there. So she has to start with the last transaction. She has to give the hash of the last transaction, right? She has to give the last transaction, transaction 4, and then the branch checks that it has the right hash. But after it checks that transaction 4 has the right hash, it can see the pointer here to transaction 3. And then Alice can give transaction 3. And then we can just traverse all the pointers back until we get to transaction 1. So everything is just like before. Alice knows all of these transactions. The difference is that these transactions now don't include any personal information of anyone. They just include these hashes. So even though Alice knows this hash that appears in transaction 2, she doesn't know that transaction 2 actually belongs to Bob and it was for $100 and so on. That information is now hidden. She knows that information only for her own transaction. So now the proof is exactly like before. She just proves that this transaction, transaction 1, is in the linked list. But after she does this, she also knows the values that created this hash. So she can actually open this hash and say, okay, now this hash says that I'm Alice, I deposited 50, and this is my nonce. So she can know only about her own personal data, and she can prove the existence of the transaction to the other branch. And everything else goes through because, well, of course, she can withdraw now because she can prove her own transaction. Every deposit can be withdrawn at most once because, again, let's say the London branch just keeps track of the serial numbers that are withdrawn. And it's really important that these serial numbers and the hash pointers, they're outside of this hash. So the design is quite important here. And M does not leak personal data for the same reason as before. It's a hash. It has constant lengths for the same reason as before. But now we also have this privacy. Now we have this as well. No client can see any other client's information. They can only see the hashes, and the hashes don't leak. But we still don't have short proofs. The lengths of our proofs are still as bad as before. So my proof is still the same as before. If I want to prove transaction I have to provide all the transactions from transaction I forward. So if I want to prove the first transaction, I have to give all of the transactions. So in the worst case, my proofs have a length of basically theta n. Okay. So how do we make this better? Let's forget about the hashes and let's just look at the data structure. What are we doing? This message M that I'm giving to the London branch, it's basically a pointer to the last transaction, right? Because we talked about this, hashes are pointers. Now I'm giving a pointer to this last transaction, and whenever someone wants to prove that their transaction is in the list, they have to basically help the London branch traverse this whole list until it reaches their transaction. So that's the problem. The problem is that I have a linked list, and basically I have to traverse this linked list until I get to the transaction I was looking for. And doing that, in the worst case, takes n steps, or n-1 steps, okay? Now, from your basic data structures courses, what is a data structure that would allow you to traverse it faster? You can just use something like a binary tree, right? So this is the intuition that I want you to have. Imagine that instead of having a linked list, I just use a binary tree. So let's say I have a root in my tree, and each node has 2 children. It's a binary tree. So it's a tree that looks like this. Okay. Now, if I have a tree like this, and if I have n elements in the tree, So let's say n nodes or n elements. What is the height of this tree? It's logarithmic in n, right? So my height is just going to be O of log n. Now, let's say that I somehow can give the London branch a pointer to the root of this tree. And let's say that every node also has two pointers. It has a pointer to the left side and a pointer to the right side. So a pointer to the left child and another one to the right child. If this is the case, then you can see that my proofs will be shorter. So if I want to prove that this node, for example, let's say I want to prove that this is in my tree. Let's say this is the transaction where I've deposited some money in Hong Kong. I want to prove that this is in the tree. And let's say that the pointer that Hong Kong sent to London was a pointer to the root. All I have to do is that I have to prove that the root is there. So I have to give the root to the London branch. Then I have to show that the root has a pointer to this left child and give this left child to the London branch. Then I have to show that this left child has a pointer to a right child and give this one. So now, as you see, I'm basically providing only one of the nodes at each level of the tree. So I'm providing a proof that has a length of log n. But I didn't tell you how to create this tree yet. This is just the intuition. The intuition is that instead of traversing a whole linked list, which takes linear time, I just want to be able to traverse a binary tree, which takes log n time. Okay? Now, how do we actually make this kind of tree? This is what we call a Merkle tree. Okay. Now, here's how this works. Let's say that I have a bunch of transactions, transaction 1 to transaction 4. Now, in my transactions, I'm just going to put the personal data. So basically, I have, let's say, I don't know, personal data, let's show it with D. So I have D1, D2, D3, and D4. And basically, D1 is the personal data of Alice. It's basically the string that says Alice deposited 50 and her nonce was N1. So that's what D1 is, right? And similarly for all the other ones. So for example, D4 is just Dave 10 N4. Okay, so D4 is just going to be Dave deposited 10 and his nonce was N4. Okay, I want to create a binary tree that contains all of these pieces of information, D1 to D4, kind of as its leaves, but not exactly. So here's what I'm going to do. I'm going to create a leaf for each one of these. So I'm going to create a node in my tree. And in this one, I'm going to put the hash of D1. In this node, I'm going to put the hash of D2. Similarly, I'll just put the hash of D3, the hash of D4. Okay. Now, I want to create a binary tree. So there should be a node that is the parent of both of these. And let's give this a name. Let's call this one L1. So L1 is just the hash of D1. L2 is just the hash of D2. I have L3 here and L4 here. Now I create a parent that basically has the hash of L1 and L2. So I do this. Hash of L1 concatenated with L2. And I make it the parent of both of these. And here I do the same thing. I have to scroll up in order to be able to write. So hash of L3 concatenated with L4. Okay. Let's give this some other name. So I don't know, let's call this one B1 and let's call this one B2. I will finally have a root, which basically has the hash of B1 concatenated with B2. And this is my root. Let's call it R. Okay. Let me just clarify something here. So I have a bunch of pieces of data, and all of these are strings, D1, D2, D3, D4, right? So I'm taking the hash of D1, I'm calling that L1. So L1 is also a string. It's just the hash of D1. L2 is just the hash of D2. So I then take these two strings, I concatenate them, and I take their hash, and I call that B1. So if I want to expand this, B1 is basically the hash of D1 concatenated with the hash of D2. That's what B1 is. Okay, and similarly, B2 is the hash of D3 concatenated with the hash of D3. Now, finally, I'm going to use my root hash, which is called also the Merkle root. So this whole tree is called the Merkle tree after its inventor, and the root, we always call it the Merkle root. I'm going to use this root as my message M. So this is what the Hong Kong branch is sending to the London branch. Now, the first thing I want you to see is that when I send this message M to the other branch, I'm basically committing to everything in this tree. I'm committing to all of the data points, D1 to D4. Because if I later want to change any of them, let's say I want to change D2, this would also change L2 because it's just the hash of D2. But if it changes L2, it will also change B1. And generally, whenever any node in this tree changes, it also changes its parent, because you have to recalculate the hashes. So this means that when I'm giving the hash of the root, I'm committing to everything in this tree. I cannot change any of the entries in this tree. Okay. So that's good, because it means that I can just send this root hash to the other branch, and I have sent a very short message, a message of constant length, but I'm now sure that that message has enough information to commit me to every one of the transactions. Now, let's say that someone wants to prove that their transaction is actually in the list. So what kind of proof should I give to Alice so that Alice can prove that D1 is actually in this tree? So Alice should be able to go to the London branch, and she should be able to basically let the London branch start from here and then go to B1 and then go to L1, so that they're convinced that D1 is there. So the information that Alice needs to know is going to be what? Well, she needs to know the root hash. So needs to basically know M, or let's say this, right? But let's say that she knows M and the London branch also knows M, but now Alice wants to prove that B1 is the left child of M. Okay, how can you do that? Well, you actually also need to know B2, right? Because the only way I can prove that B1 is the left child is by providing both B1 and B2 and saying just take the hash of B1, B2, and that gives you the hash that you already have here. It gives you R, right? So Alice needs to know this node. Alice needs to know R. She needs to know B1, but she also needs to know B2. And the role of B2 is to just prove that B1 is the left child of R. Okay. So now that she has provided this information, the London branch has verified that B1 is the left child of R. But B1 is just a hash at this point, right? Now Alice wants to prove that L1 is the left child of B1. But in order to do that, she also needs to know the right child. She also needs to know L2. So if she provides both L1 and L2, then the branch can just compute the hash of L1 and L2 and verify that it was correct, which means that L1 is the left child and L2 is the right child. So she needs to know L2, and she needs to also know L1. And at this point, when she gives all of this information to the London branch knows that L1 is in the tree. Now, L1 was just the hash of the personal data of Alice, and Alice knows her own personal data. She knows that D1 was basically Alice, 50, and N1. So she can just provide this, And then at this point, it's proven to the bank that this deposit was actually in the list and it was actually in this tree. So now let's do it for someone else. Let's say that Carol wants to prove it. So I want to prove this third transaction. Again, I have to prove the root. I have to prove that B2 is the right child of the root. But in order to do that, I have to also know B1. So she should also know B1 and B2. But at this point, B2 is proven to the bank. So she wants to prove that L3 is the left child of B2. But to do that, she needs to also know L4. So she needs to know L3 and L4. So this is the proof that I'm going to give to Carol, to the person who's done the third deposit, and so on. Now, in general, this might not look great when I have only 4 deposits because the proofs seem to be long. But in general, if I have a long tree, basically my intuition holds. I can start at the top of the tree, and I just have to provide the path that goes to my particular leaf. But the difference is that whenever I'm providing some node, I have to also provide its sibling. So I'm not going to just give proofs of length log n. The lengths of the proofs are actually 2 times log n. But that's fine. I don't care about just the constant factor. It's O log n anyway. So I can now have proofs whose lengths are just O log n. So every pi, now, if I take any proof pi, the length of this proof, it's in O of log n. More specifically, it's twice the logarithm plus 1 plus 2, whatever. Okay. Nice. So this is what we call a Merkle tree. And it finally now satisfies all of our requirements. So first of all, it has short proofs. Short in the sense that the length of the proof is O log n. We will later on see how we can actually decrease this to even constant time when we talk about digital signatures and other things. But for now, this is short enough for us. It also protects the privacy because you see, any one of my clients would just see some of the hashes in this tree. But these hashes, they don't contain any personal information. So in my tree, I'm not putting any of the actual personal data. I'm only ever putting the hashes. And all of my hashes have nonces in them. So it also satisfies the privacy requirement. And these previous requirements, it's also kind of easy to verify. So the message that is sent from one branch to the other branch is just the hash of the root. That's constant size. Of course, it doesn't leak any information. None of our hashes leak any information. And every depositor can prove that their deposit exists by just proving the path from the root to their deposit. So that's fine. And when we say each deposit can be withdrawn at most once, that's also easy because the London branch can basically keep track of the hashes of all the deposits that have already been paid out. And you don't pay out for the same hash more than once. Or you can keep track of the paths that have been paid out and you don't pay for the same path more than once. In any case, it's easy to keep track of these things. Okay. But we still have another problem, and this is a problem that we will solve in future sessions. And the problem is that this is not in real time, right? So in order to create this whole tree, I need to know all of my transactions. So the way this actually works is that on day 1 in the morning, everyone goes to the Hong Kong branch and deposits their money and gives their nonces and everything. And then after all the deposits are done, only then the Hong Kong branch can create that tree, the Merkle tree. So they create the Merkle tree, they send the hash of the root to the London branch, but again, only after they have created the Merkle tree, they can give the proofs to the clients. So when the client makes a deposit, they're not going to get a proof immediately. They're going to have to wait until everyone else does their deposits too. And then only at the end of the day, they each get their proof. Okay. So we have this problem here in general. Now, let's forget about our use case and let's just focus on Merkle trees. So we saw how we can prove that a particular item is in the leaf of a Merkle tree. I can just start at the root, prove the path. What if I want to prove that a particular item is not in the Merkle tree? Can I give those kinds of proofs? So right now, it seems impossible, right? Because, I mean, how can you prove that something is not there unless you know everything, unless you can prove every single element that is there? If you know all of the hashes at every level, and if you know D1, D2, D3, and D4, you can prove everything that is in there, and then you can say nothing else is there, right? But in general, if I give you some other number, D5, and I ask you, is D5 in this tree or not? There is no way you can give a short proof that D5 is not in the tree. But we can solve that by a very nice trick. And this is what we call a sorted Merkle tree. So the idea in a sorted Merkle tree is that I'm just going to create a Merkle tree. But when it comes to the leaves, when it comes to the data elites, D1 and D4, I'm going to sort those. Okay. So I'm going to have the exact same thing as here. Let me see if I can just copy this. I'm going to have the exact same thing. Now it's going to be sorted. So it means that D1 is going to be less than D2, less than D3, less than D4. And in general, I can do this with n elements, of course. Now, why does this sorting actually help me? Well, first of all, how do I sort strings? I can just sort them in lexicographic order. So even if you think of these not as numbers, but as just sequences of zeros and ones, you can sort them anyway. So we have an order. And now let's think of them as numbers for a second, because for this example, it's easier to do with numbers. Let's say D1 is 2, D2 is 5, D3 is 8, and this one, D4 is 10. And suppose that I want to prove that there is no 6 in here. How can I prove it? Well, I can just prove the existence of D2 and D3. I can just prove the existence of 5 and 8. Because when I prove the existence of 5 and 8, I'm not just proving that they exist in the tree, I'm also proving their location in the tree. So if I prove that 5 is here, which I can do, and I can give a proof of length log n. And then if I can also prove that 8 is here, because I've also proven the location, I've proven that 8 comes exactly after 5, which means that there is no 6, there is no 7, right? So this is how we can prove that a particular value does not exist in a Merkle tree. If I just sort all of my values, and if I just prove the previous value and the next value. Okay. But now, of course, the next problem and what I want you to think about is that suppose I want to prove that a particular value is not in my tree, but I also don't want to leak information, right? Because here I have a problem, and the problem I have is that I wanted to prove that 6 is not in my tree, but then in order to do that, I had to prove that 5 and 8 are actually in my tree. But that's leaking 5 and 8. That's leaking some information, and maybe I don't want to do that. Maybe I just want to prove that a particular number is not in the tree, but I don't want to leak any information about the numbers or the data that are actually in the tree. Can I do that? Yeah, so the idea is actually, well, yes, exactly. So instead of sorting based on the Ds, let's just sort the Ls. Let's just sort based on the hashes. right? And then when I want to prove that a particular item is not there, I just take its hash and then I prove the previous hash and the next hash. And that proves that this particular hash is not there. And when the hash of this item is not there, that item is also not, right? So that's pretty easy. Yeah, but in general, this is like a factor of two. Well, not a factor of two exactly. It's a little bit worse than just proving the existence of something, because now I have to prove the existence of two things. So if I just wanted to prove the existence of 8, I have to provide R, B2, B1, L3, and L4. But now for 5, I have to prove R, B1, B2, L1, and L2. So actually, in this particular case, again, because my tree is really shallow, in order to prove that 5 and 8 exist, I have to prove L2. Okay. Now, here's a problem that I want you to think about. Suppose that I want to play rock, paper, scissors, but I want to play it over the internet. So this is just something to think about, rock, paper, scissors. This was actually the homework in the last offering of this course, but I'm not going to use the same homework again. So I'm just going to give it to you. Let's say that I have 2 players, Alice and Bob. And let's say they have access to the internet. So let's say they're on a group chat and everyone else can also see what messages they're sending. So they cannot fake messages and they cannot also hide the messages that they have already sent. But let's say they want to play rock, paper, scissors. Now, in the real world, the way we do this is by forcing them to move at the same time, right? But if I just have a group chat on, let's say, WhatsApp, I can't do that. Because even if I give them a very particular time, if I say you have to write rock or paper or scissors exactly at 12:50, it might be that Bob is cheating and he just has a script that waits for Alice to write the answer. And as soon as she writes the answer, Bob takes that answer, calculates what would make him win, and immediately outputs that. So if Alice is playing rock, Bob would immediately play paper. And you cannot tell the difference between this kind of cheating and just basic network lag, right? So the question now is, how can we play rock, paper, scissors in a secure way, in the sense that we want to make sure neither side can cheat? Okay. And actually, I want you to think how this relates to the example of the auction that we saw before. Because in some sense, you can also think of an auction as a game. And the idea there was that you should also move before knowing your opponent's move. And here it's exactly the same problem. So I have to make sure that Alice moves before knowing what Bob wants to do. And I have to also make sure that Bob moves before knowing Alice's move. Okay, so I'll see you tomorrow.